Thanks a lot, Charles, for the introduction. As you heard, my name's Quinn Reynolds. I'm from Mintech in South Africa. I'm going to be talking a bit about the work that we've been doing for the last 5 years or so on developing a bit of a software ecosystem for modeling different aspects of furnace tapping systems. I think we've really found that HPC has played a very big role in this work, so I hope it's going to be interesting to you. Just before we get started, here's a bit of background about Mintech, just in case you don't know. We're a South African government research institute. We're one of the science councils, and we do applied R&D and technology transfer in the field of mineral processing and metallurgical engineering. I'm part of the pyrometallurgy department, which pretty much covers all aspects of high-temperature metallurgical processing. In particular, as my 6-year-old daughter likes to say, it's where Dad and his friends get to play with lava. So let's get started on the topic at hand. Submerged arc furnaces, or SAFs, are used in the production of many different metallurgical commodities. In ferroalloys like high-carbon ferromanganese, these units consist of a circular shell lined with refractory bricks to contain the process, and they've got 3 large vertically mounted self-baking graphite electrodes for the input of electrical power. The furnace is usually operated with a deep layer of unreacted feed material called the burden, that sits above this pool of molten products that collects in the base of the vessel as the feed materials melt and react. Typically, these things are running at about 1500 degrees centigrade, so it really is a very high temperature process. Those molten products are usually in the form of a slag, which is an oxide-rich material that's like the stuff that rock's made out of, and alloy, which is a metallic product that's usually the actual thing of value. So now you've got to get them out of your furnace somehow to make sure that the process keeps working, and this is done by something called tapping, which involves periodically opening a tap hole channel in the furnace wall by drilling or thermal lancing, allowing the products to drain out into storage vessels, and then resealing the tap hole by injection with a hydraulic clay gun or something similar. So tapping is one of the most potentially hazardous operations on any furnace, and any unexpected event during a tap can really rapidly escalate into a dangerous situation for people and equipment. So some understanding of how tapping systems work is therefore of a lot of interest, not just as an academic research problem, but also as a practical tool for protecting people and improving the quality and reliability of the operation. So if you take a look at tapping systems on most smelters, you can break them up into several sections. The first part of the tapping system on the left there is the furnace itself and the tap hole. For commodities like ferromanganese, a single tap hole is used to tap slag and metal phases simultaneously, but other processes sometimes use separate tap holes for different products. It just depends on the process. And the next part of the tapping system is the transfer launder system. These are basically open-top channels that direct the flow of molten material away from the furnace and into the storage vessels. And the last part of the tapping system is the storage vessels themselves, which contain the material that's removed from the furnace. In most processes, these are large cylindrical or conical ladles, also lined with refractory material, and they've got gravity overflows in the rim to allow multiple ladles to be arranged in a strand. So to give you an idea of what it's like working around tapping systems, here's some photographs that were taken by my ex-colleague, Dr. Jolette Steenkamp, at industrial ferromanganese smelters here in South Africa. You can see it's an aggressive environment. There's a lot of thermal radiation, gas and dust emissions, free surface flows with splashing and combustion. It's really not a nice place for people or machinery or instrumentation, even when it's working properly. And that's why we like to use numerical and computational models to study these things. So we've been spending a lot of time lately looking at furnace tapping systems using models. We started off with computational fluid dynamics and multi-physics models because they can give you a huge amount of information at an extremely deep level as to what's going on in a flow process, which this fundamentally is. Of course, it also helped that we'd already been working a lot with models like this, so we could kind of hit the ground running. Like any tool, CFD is good for some things and it's bad for other things, but it was a reasonable place for us to start off. So back in 2017, we started trying to strip the problem down to its absolute simplest form. So here we're showing a transient 3D simulation of a single-phase flow entering a long straight channel, and we're really looking in detail at how the turbulent flow triggers in and around the channel entrances. This is about the most basic version of a furnace tap hole that you can imagine, but it's already telling us quite a lot about what's going on here. By the way, just note the little HPC star up there in the title of the slide. You'll see that pop up quite a bit in this presentation, and it's just letting you know that we needed to use high-performance computing to generate the results that we're showing. So by characterizing the single-phase tap hole flow in terms of a pair of dimensionless variables, we could then run a matrix of different simulations and really start to get to grips with the space that that problem lives in. So the gray hatched area here is just showing the transition region from laminar to turbulent. We also overlaid some typical ranges for the different types of materials that you might tap from a smelter. So we've got slags and metals obviously there, like I mentioned before, and also mats, which are molten metal sulfides. And this kind of parameter sweep study is really only possible with HPC resources. That's where it starts really showing its value. So after that, the next step was to try and extend the problem out a bit, make it a bit more realistic and similar to what's going on in real furnaces. So this was our original simplified tap hole geometry, basically just a plenum entering into a straight pipe section. The first thing we did was have a look at what happens to flow in worn tap holes. We got some measurements. This was actually from a platinum smelter, and we reconstructed their actual tap hole geometry inside our models, and this is kind of what it looks like. Basically, the increased diameter is just as a result of the wear of the tap block through which the tap hole runs. And that happens as a result of drilling and lancing to open the tap hole, and they're very aggressive thermal and mechanical processes. And you get a lot of thermal and mechanical wear from the material flowing through it as well. So here we're showing some results from flow simulations in the worn tap hole, again, single phase only. In the video on the left, you can see the flow velocity field, and on the right, we're showing a post-processed calculation of the shear stresses on the tap hole walls. Those shear stresses are kind of interesting for furnace operators because it tells you something about where that hot process material is going to be most likely to wear the tap hole even further. So now here we're just showing the average velocities at the tap hole outlet at the end of the simulation, but now for a different set of cases that we ran to look at the sensitivity of the model to changes in operating parameters and also degrees of wear. It's pretty obvious, I think, from those graphs that the head pressure is the dominant variable in this particular case. And that's, pretty much what you'd expect from basic fluid flow principles. It's nothing too surprising. What was quite interesting, though, was that when we changed the tapping temperature, there ended up being very little effect on the flow. And that's mainly because the material properties of the material that we're looking at here, don't actually change very much with temperature, or when they change, they compensate for each other. So it was quite interesting to see. So then we moved on a bit to looking at more advanced CFD models of multi-phase flow inside the furnace tap hole. It's a lot more realistic in cases where different products like slag and metal are being tapped simultaneously, and these are immiscible fluids. We also started including a non-uniform porous bed inside the furnace to represent the burden layer and how that restricts the flow. And that extra physics introduces some interesting dynamic effects. So here, the interface inside the furnace starts off being below the level of the tap hole channel, but as the flow starts, it actually gets pulled up against gravity. And because the flow of the slag in and around the tap hole entrance is obstructed by the porous particle bed inside it, as soon as the metal is able to reach the tap hole, it's got so much momentum it actually pushes the slag out the way quite substantially. We also started looking at some other parts of the tapping system using these same tools. So here we've got some animations of results from multi-phase CFD models of tapping launders with slag in orange and metal in blue. I don't know if you can see it too clearly on there. And basically in this case what we were interested in seeing was what happens if you have a lot of phase mixing between the slag and the metal inside the tap hole before it comes out into the launder. And what we really saw was, even though these launders are very steep and the material doesn't spend very much time in them, the containment and confinement of the flow against a surface is enough to force quite a lot of gravity separation, almost regardless of how well the inlet stream is mixed. This was something that was really worrying the operators, but it turned out to be actually not that important. So a big chunk of the multi-phase work was also around understanding what goes on inside tapping ladles that last, those big containers that the material pours into after it comes out of the furnace at the end of the tapping system. So this is just an example of the models that we built for that. On the left there, you can see an animation of the phase interfaces in the first ladle in the strand. Again, orange is slag, the lighter slag material, and blue for the metal, which is denser. And it just shows some of the complicated fluid dynamics that go on during ladle filling. So on the right, we've just got a plot of slag and metal outflow at the ladle outlet, and that can give us a more quantitative picture and quite a good data set in terms of what's going on. One wrinkle in this particular part of the process is that the inflow stream disturbs that slag-metal interface in the ladle a lot. So when the interface starts getting near to the overflow, you start getting quite a lot of metal entrained in your slag as small droplets. And by running multiple simulations as numerical experiments, this is something you can quantify quite nicely with CFD models. And that gives us some useful data to work with in other applications down the line. And speaking of other applications, let's move on to the second leg of our studies. And that was really about developing lightweight reduced order models for tapping systems. We did this by combining fundamental descriptions of the main physical phenomena that were going on with some real-world observations on furnace plants and also information from the CFD models. And the aim here was really to get something that contained the bare bones of the problem physics, but without the massive computational cost of CFD. Again, it's important to remember that things like ROMs have good and bad points. It's horses for courses. You have to make sure you use them in the right way. A lot of the ROM work really focused on what was going on in the tap hole and inside the furnace, since in many ways that's the most physically complex part of the problem. We developed some simple submodels based on descriptions of physical phenomena like dynamic mass balances on slag and metal inside the furnace, pressure balances between interior and outlet, multi-phase flow effects like interface deformation, and porous media effects like inflow through the burden layer. And what you get at the end is quite a messy and very nonlinear set of first-order ordinary differential equations, where tapping flow rates are a function of levels in the furnace, and the levels are changed by the tapping flow rates. And this is the kind of result you can get from the tap hole ROMs. Here we're showing a silica manganese furnace that's being tapped at regular intervals with tap timing and other parameters that are actually coming in from an industrial data set. And the top graph is showing levels of slag and metal inside the furnace over time. And the bottom one is showing the tap masses of the different materials, so how much has actually come out of the furnace. The taps are shown with the gray bands, which are sort of visible there. And those are the periods where the tap hole is open, in between it's closed. And you can basically see how the tap mass builds up over time inside those bands. So stepping back and looking at the operational picture a little bit more, you can see that we're getting pretty good agreement between measurement and model, at least in the metal masses in the graph at the top there. This is a comparison against an industrial furnace, and the agreement was around 90% in this case, which we thought was actually quite good for such a simplified model. The agreement's quite a bit worse in the slag masses, which are at the bottom there, but it's important to note that this particular plant doesn't measure slag masses directly, and that's quite common in industry. They kind of estimate them using a simple thermodynamic or mass balance calculation, and therefore you've got to take the data with a heavy pinch of salt. The slag masses do at least track the right long-term trends as they're going along. So another interesting way to use ROMs is to do sensitivity studies. Here we basically looked at an integrated tapping system flowsheet model, including the furnace and tap hole, the tapping launder, and the storage ladles connected in series all together. Basically what we do for each pair of input and output parameters is run the model for a few hundred taps, make very sure that the initial conditions have all died away, and then measure the change that's produced in the output from small changes in the input. And the final result is this gigantic mess. Don't worry too much about the details, but suffice to say that what it does is it points us in the direction of which parameters have a biggest influence on the behavior of the overall system. And it's quite useful stuff to then go back and start exploring in laboratory experiments and other things. So now you're probably starting to think, well, you know, this is cute, but you don't need any HPC for this, right? Well, this is where it gets a bit interesting again. So in this next study, we simulated a tapping system with some reference parameters, but at every tap we'd introduce a small random perturbation on the parameters, up to maybe a few % of the value. And that's similar to what you'd expect to happen on a real furnace operation, where there's a small degree of variability that comes into the operation naturally. But to do the statistics properly, it turned out we really needed to run a very large, effectively Monte Carlo simulation using these ROM models. And for that, we definitely did need HPC. So sorting out all the results into probability density distributions, this is kind of what you can get. So here we're showing all the different output variables from the model. From top left, it's the metal and slag levels in the furnace, and the metal and slag tapping flow rates. And from bottom left across, it's the tap mass of metal and slag, the metal losses, and the tapping time, which in this case was fixed at 30 minutes for the reference model. And then you can do nice things, like starting to test out different control strategies for your whole tapping system, and you can see what happens. So here we were trying something that's often done on real operating plants, and that's that you measure the level of slag in that first ladle, and you watch it, and it gets less and less and less, and at a certain point, you stop your tap to try and limit the losses of metal to the other ladles in the strand. And the stats show that controlling on layer thickness actually really disrupts the system quite a lot. It pushes a lot of variability into systems that didn't have variability before. And although the metal losses are indeed controlled very tightly, the rest of the variables are all over the place. And that could definitely have some unintended consequences for your operation. So another way to use the ROMs is to map out the kind of phase spaces that these big problems live in, which lets us visualize dynamics rather than statistics. So on the left there, we're showing the deviation in the mass of metal in slag inside the furnace between successive taps, with the natural equilibrium point shown by that dot at the bottom left. And on the right, we're showing some tapping trajectories. So these are paths that the system follows in that space as it's recovering from disturbances or non-equilibrium conditions. And those multiple taps then converge on that equilibrium point in different and interesting ways. And while those models are for a particular set of parameters, and those can be run quite nicely on a desktop computer, we decided to go a step further with it. So these graphs are showing the values of the slag and metal inventory inside the furnace in tons at the equilibrium point. So that was that one dot on the previous graph. But now we're calculating where that dot is for a very big sweep across some of the model parameters. In this case, it's the tap timing with the tap duration on the x-axis and the time between successive taps on the y-axis. We needed to run about 40 million tapping simulations to generate these results. So on a real furnace, that's about 20,000 years of operation. So we're not going to get a data set that size out of industry anytime soon. So yeah, did we need HPC here? Yeah, we kind of did. So that really then brings us maybe to a look into the future of tapping modeling, and perhaps fittingly for the theme of this year's conference, which is looking at whether we can use AI ML tools to build some pragmatic models that can be easily used in everyday life on operating plants. And again, these have got a lot of desirable and undesirable characteristics, and probably the most important thing is really to know when it's a good idea to use them and when it really isn't. And probably the single biggest problem we have with using data-driven methods in pyrometallurgy is that the data itself is typical real-world industrial plant data. If anybody's had to work with that, you'll know what I'm talking about. It's incomplete, it's full of errors, it's recorded at weird and inconsistent intervals, and it's basically a complete mess that you have to try and homogenize before you get it into these tools. Overlaid on top of that, we are extremely data-starved in pyrometallurgical applications. Our data sets are actually very, very small because it's difficult to measure things. And the processes themselves also work quite slowly in real time. Like I said, one furnace operating for 20 years might give you a couple of thousand data points. And that's not really enough for good ML. But, we tried anyway. So just first a caveat, I should mention that all this work is actually not mine. It was done by my machine learning postdoc, Dr. Alexei Cherkaev, while he was at Mintec a couple of years ago. We basically got a fairly good data set from an industrial furnace operator, and after doing a lot of tidying up on it, Alexei then applied some ML tools and tricks to reconstruct the high dimensionality of the data and also remap it in regularized ways. After that, we then took the usual approach of grouping the data into training and testing subsets. The training sets are used to actually fit the model, and the testing set is used for model validation. Alexei applied a very simple linear autoregression model, but he was combining it with feature selection using the lasso ridge regression technique. Please don't ask me about that, but apparently it's very cool. There are some graphs of the results that he got out with the true versus predicted values on the left, and a time series of the true versus predicted values on the right. So the accuracy of the tap mass predictions in the case of the ML model was about 72%. It's not too bad, considering that we're talking about a very small data set here. The main predictor turned out to be power input to the furnace, and that actually matched up very well with what we see in the fundamentals-based approaches like the reduced order models. So this work is still very much in its infancy for our applications in furnace tapping and other things in pyrometallurgy, and I think we can definitely do a lot better here. In particular, there's an intriguing shift in our field anyway towards ML models which have some physics awareness in them. So they're basically constrained not only by the data they're given, but also by the appropriate physical laws that govern the processes actually being modeled. And we're looking forward to getting our teeth into some of these approaches as the next step beyond what we've done already. And I'm pretty confident it's also going to end up growing into one of those applications that needs a fair bit of HPC in the future. Maybe not HPC as we knew it, but HPC nonetheless. So I think I can probably wrap up a little bit here. Basically, we've spent the last few years going on a pretty deep dive into these furnace tapping systems with numerical models of various sorts as our guides along the way. On the surface, it's one of those things that really looks like an incredibly simple process, and it looks a bit boring, and you think, okay, it'll take me 2 weeks to do this, and then I can move on to something else. And we've been doing it for 5 years. So, but the reality is that there's a surprising degree of subtlety and complexity that comes into it when you actually start looking at these problems from all these different angles. And it's highly relevant in our industry. We're trying to improve efficiency, reduce carbon emissions, all of these good things. And almost every single metallurgical furnace on the planet manages to do some kind of furnace tapping as a routine part of their operation. So it's got a lot of broad application. And for us, it was really amazing just how much better we could study the problem once we brought high-performance computing to the party. I think everything from traditional HPC workloads like CFD through to the unexpected value in doing massive statistical and parameter space sweeps with ROMs, and through to the HPC workloads of the future like AI/ML. It's really given us an astonishing level of insight into this supposedly simple problem, and we look really forward to seeing where it takes us next. So that's it from me today. Just some quick acknowledgements to Mintech and CHPC, of course, and also to the team of academic and industrial partners who have worked with us on tapping problems for so long. And it's really been a fun ride. We've enjoyed every minute of it, and we hope we're going to be able to do a lot more. So thank you.
Thank you very much, Quinn. As ever, very entertaining and very interesting and to the point. Are there questions, please? Are there welcome?
Thanks very much, Quinn. That's very impressive work. I know very little about slag, but I'm really curious in the kind of material definition. Do you define it using rheology, or is there a sweet spot between it or shear perhaps use this non-Newtonian material?
Yeah, that's an excellent question. In fact, my colleague from Samancor and I were just talking about this yesterday. Traditionally, we treat all of these materials as pretty much classical Newtonian fluids. One thing we're reasonably certain of is that that's not what they are. So it's very much something, unfortunately, because we're at such incredibly high temperatures, doing direct measurements is very hard. We're hoping that we can sort of hopefully leverage material science type approaches in the future to actually study some of these things, but we believe that there's a lot of non-Newtonian behavior going on, and we probably do need to actually figure out how to incorporate that in the future. Yeah.
Any other questions?
Quinn, thank you. HPC side questions. I'm interested in how sort of peaky your workload is. So how often do you run at CHPC, and for how long, and how much resources do you use? What's your typical use profile?
That's a fascinating one, and it's one I have a lot of arguments about with our guys at Mintech, who always every now and again pop up and say, oh, let's buy an HPC cluster. And I have to explain to them that we basically need a big chunk of CHPC, but maybe once a month for 5 hours. So I think that it is very peaky, is the short answer. I think, generally speaking, our problems are not as heavy as the real flagship programs like weather modeling and a lot of the material science work. Our models aren't so big that we're using up massive chunks of the cluster, but they're still way bigger than anything we can do locally. And the reality is that, we tend to go through intense periods of use, like while we're actually concluding some research, but in between there's a lot of downtime, if you like, where you're actually just developing the whole approach, testing offline to make sure you're not going to waste resources when you step up and things like that. So, yeah, very peaky.
Are there any other questions? Right, I'd like to ask a question from wearing my CHPC hat, which is, what do you need from us to be able to do this better?
Keep doing what you're doing, for starters. I think we're one of the sort of early users of CHPC, and I still remain ridiculously amazed that we get a resource like that essentially for free in exchange for some publications. But in all seriousness, I think our workloads are quite diverse, or they're becoming quite diverse, I would say. If you'd asked me this 5 years ago, it would be give me a bigger cluster with CPUs in it. Nowadays, I think we probably need a bit of a balance, and probably if you ask me in 5 years, I'm going to be raving about GPUs and other things. So I think it's a bit of a moving target at the moment, Charles, but if you build it, we will come. Cool.
Right, so when I was with CHPC, I used to support a lot of the chemistry and materials guys. And of course, effective use of HPC is something I'm going to speak about today, right? Because there's still a lot of you that are not using that machine the way it's supposed to be used. So, right, so just a brief intro. Now, when we see this sign, our good old, ESCOM. Everybody sees this, first thing you think, okay, load shedding, of course. And then we think about generators, and then a lot of us get the dreaded email from Werner. Oh no, the machine is going to go down. There's so many nodes off. Now, Werner kind of spoiled my presentation because very recently he sent another email, which actually made us quite happy, that it's not a thing anymore, right? So great, the whole machine is still up. But again, as I say, if you're not making effective use of the HPC, you're ruining things for people that actually can use it properly, right? So we're going to touch on two of my projects that two of my master's students are doing. And I'm just going to show you how we actually now sort of benchmark things to make sure that we're using the machine properly, right? So the first is a project which we did where we were just trying to go green. Everybody's all about the green now. So the guys tried to make this compound. This was made experimentally, and they used water as solvent for the second step, right? It's a two-step reaction. But in the first step, they used dichloromethane, which is not so green. So we wanted to see, is it possible to get both these steps to actually work in water? So that's exactly what we simulated then. So we broke this reaction up into 2 steps, and then we did the simulations, right? So for this, we made use of Gaussian, and there's all the nitty-gritty about the DFT and the level of theory and the basis set and things that we made use of. And then we also did some energy corrections just to get the barriers looking a bit better. Right, now, this is where the stuff comes in, right? So when you work on HPC, you need to make sure your application is performing properly and that it's scaling well. Gaussian is not a great scaler, right? It doesn't scale very well. So if you look at the numbers that I have here, there's not very big differences, right? So specifically, we can look at this one, right? So I just did different sets of calculation to just check. I did one where we optimized only, take the structure and do a frequency calculation, and then one where I did both together. I see these days, the numbers are actually more or less additive. So whether you're doing things in pieces or you're actually combining everything, you get about the same timing, which is good, right? So what you will notice is, if I move from 1 node to 2 nodes, this is in seconds, right? So it's not a very big difference. It's about 30 minutes that you're going to save if you're running on 48 cores. Then the time actually gets, there's not much you're saving anymore as you get increase the number of cores. So ideally, fine, especially when we had the load shedding issues, you know you're going to sit in the queue, right? So do you want to queue for a day to save half an hour? That doesn't make sense, does it? So rather just run it on the 1 node, use the 24 cores, and at least get a result on the same day. That half an hour you're saving is not much of a gain, right? So you have to be smart with these simulations. And especially all of you guys here, majority of you are students, so you have deadlines. You want to finish. You can't be sitting in the queue when you're trying to finish your thesis or whatever, right? So just be smart when we're running this stuff. Okay. So as I said, this reaction is what we did, right? So these were the 2 products that were formed. So as I showed you in the reaction before. And what we did was we found these barriers, right? So typically, when it comes to these barrier calculations, you want the barrier to be as low as possible for the reaction to proceed quickly, right? So in this case, we can see that the barrier is like 29.26 for when you're doing that in the solvent, which is dichloromethane. The blue line is then water, and then there's another line there which you can't see, that was the gas phase, right? So you can see there's not a very big difference between the two, between your gas phase, between your dichloro and water. So it is possible that this reaction might proceed in water, it might just be a little slower, basically. Right? And then the second step, we proved that actually, yes, this works in, when you do some corrections, then it actually does work where you now get the barriers to drop a bit, right? So you have to apply correction afterwards. So this is just the transition state that was isolated. As you can see, that was what was happening, right? The bond was breaking and a bond is forming. And then the second step, again, we did DFT, but the barriers were extremely high here. So like 40 somewhat, which tells you that the reaction won't go, but we know it happened because it happened in the lab. And then when we did some corrections, we found that things actually dropped a bit, right? So again, here, you can see water is now lower. The barrier is lower for water than for dichloro, so this is why the reaction happens. Right, and then this was the transition state isolated here. And with this one, we got something strange. It was a barrierless transition state. So it was the first time I ever saw this. It was quite strange, but it actually does happen. So, Okay, then the second project is by my master's student who's got a poster here. So later today, you can go have a look if you want more info. But here we were looking at antimicrobial resistance. So we're trying to find things that would basically be used for the resistance that people are building up to ARVs. So when you have your antiretrovirals, the bodies are now currently starting to build immunity to some of these drugs. So we're trying to find alternatives, right? So this is the main focus of this project. And here he is making use of what's called NNRTIs. So those are the inhibitors that we were targeting to try and find drugs for them. Right, so these are the known drugs for these NNRTIs. And we said, okay, we're going to take these known ones, and then we're going to try and train a model for these things. So again, we use HPC, right? But it doesn't mean if you have access to the CHPC that every single calculation needs to run on the CHPC. So, no, again, misusing the system, right? Don't do that. So, if you have machines, like, look, okay, fine, I've got some gaming machines that we now purchased recently. So we just run stuff on there. There's certain things you can do on your local machine, which doesn't need HPC, because you're actually going to waste more time sitting in a queue, or it's not even going to run faster if you're running on the CHPC. So certain things you can just do local. Do it on your local machine, and then only the bigger jobs is what you need to run on CHPC. Right, so that's exactly what we did here. So we did some docking studies, we ran it on our local machines, and then we trained the model using QSA. Once we trained, we tried to make predictions for new molecules, and then that part there is what we then dumped onto the CHPC because we needed GPUs there fast enough to run the dynamics. Right, so everything else was, and then the Gaussian jobs also, we ran on the CHPC. Okay, so this is just an image of when we initially did the docking of the protein that we were interested in, and this is just a validation, right? So you get a crystal structure, which typically has something inside it, and when you do your docking, you need to just compare back to the crystal to see, does the docking protocol work, or is it rubbish, basically? Right, in this case, it worked quite well, and we got various different scores for the drugs that are already known. So then we made predictions using our QSA model, and because we only had a very small data set with actual activities, because that's what we were fitting against, we then decided we'll run that also on the local machines. When your data sets get very large, because this is similar to machine learning, right? So when you have very large data sets and you want to exploit the GPUs, then yes, then you'll run on the CHPC. But this wasn't necessary in this case. So here we actually had different classes, and we found that this class produced the best sort of fit. So from that, what we did was we tried to predict new molecules by doing something simple. We take the drugs that are already there and literally just add a group to it by using a method called enumeration. So you just enumerate by adding a small molecule onto it, and let's see, is it better, is it worse? Because from a synthetic perspective, if people were to make it, it's easier just to add a single group than to make a big, massive new drug, right? So that's what we did. We found a few potential hits. So when we did predictions, this is just the predicted activities for these drugs that are known, which don't have known activities, but they are known drugs, right? So not all drugs actually have activities that people can they measure experimentally. Unfortunately, these ones didn't, so we had to predict them. Right, so we found predictions, and then we predicted for our new molecules, and then we did the dynamics. So the molecular dynamics was just to see, does the drug that we've designed stay inside the site that we're looking at, right? Because if it stays inside, it's got the potential to be a good drug. If it pops out, it's a problem. Then it means it's not going to work. So here you'll see we ran like 200 nanoseconds, and we can see the RMSD values are not too high, right? So your protein is quite stable, and so too is then the ligands. 4 angstrom, it's kind of cutting it close, but yeah. You'd want it to be a bit less than that. Right, and again, here we benchmark. Now, if anybody knows me, you will know, I love the GPUs at the CHPC. I fought for those GPUs, and I don't like people that don't know how to use it properly. It's a problem. So, so when we run on the GPUs, you need to know, first of all, you have a limit of 12 hours wall time, right? You cannot get access to more than 12 hours. So, when you do any dynamic simulation, your dynamics package will tell you how many nanoseconds you expected to get in a day. In this case, we were using Desmond as the MD package. Now for Desmond, it told us, okay, say for that molecule, 150 nanoseconds in a day. Now, we're all scientists here, simple math. If it's 150 nanoseconds, you cannot expect to run a 200 nanosecond job if it can only give you 115 in that time, right? Also, because you only have access to 12 hours, you actually only can run 57 nanoseconds in that 12 hours. So don't submit a 100 nanosecond job only to say, 12 hours later, whoops, I must resubmit this job, I must resubmit this job. And you're going to go on, just wasting the resource and getting nothing out. Because no checkpointing, right? The checkpoint will only be written after 50, in this case. So please make sure you check before you run those jobs, so that essentially, you will then be able to run pieces of 50 to make up your 200. Right? So you can just run 4 separate jobs, 50, 50, 50. Right? And then it gives you the job. Also, one thing to note, when it comes to Desmond jobs, there is a limited number of licensing at the CHPC for the molecular dynamics. So often, you might run a job and you'll see like within a few seconds it dies. And what you should go do is go and look in the output file. You will see something saying something about a license, which typically means that those 4 licenses that are available are already being used. So there's 4 people running somewhere. And because they're running, your job won't run. You have to wait for one of them to finish. But then, basically to conclude here, so as I said, you do not need to use the greatest number of cores and the highest available wall time in order for you to run simulations, right? So if a code is serial, it only runs on 1 core. Taking it to CHPC is not going to make it faster. It's going to still perform about the same as what it performed on your desktop machine. So make sure you know your codes and that you're actually running it properly, and don't ask for the most number of cores and the largest amount of wall time, because it's not going to be faster, right? So always test to see that things are optimal. So before you start running lots and lots of simulations, just do simple tests. Just check what would be optimum for my system, and then you do the same for the rest. Right? The short gain that you might obtain from simulation, you will lose in queuing, as we've seen, as I've said, right? And this is just the thing. If you want to queue less, be smart about how you submit your jobs, because shorter wall time, you got a likelihood of getting in faster than a longer wall time. Less cores, again, likelihood of getting quicker. So these are just things you must think about, right? And as I said, and I'll say it again, don't need to use CHPC for everything. So, CHPC is great, we're not saying, we love the resource, but you don't have to use it for everything. Sometimes you can get away with just using your own machine. Right? And then don't keep running simulations if you can see it's not going to reach the desired point, like I said with the MD. If you ran it the first time and it didn't get there, don't think by resubmitting it's going to get to where you need to be. You need to know, no, I need to cut it shorter. Let me go and have a look at what's the problem. Right? And then, we know CHPC is going to upgrade, so fine. Right? Eventually, the new machine is going to come. There's going to be more resources available, right? But the problem is then, there's going to be more misuse. So, what do? A lot of you would know that there's a lot of scripts on that cluster right now, which I've written, right, before I left. So what I'm going to start doing is, I keep seeing you guys are misusing the machine. I'm going to change up those scripts that are going to start killing your jobs if they are not used properly, right? So I think that's fair. But yeah, so as a final thing, just a few acknowledgements. The UJ and CHPC for inviting me to give this talk today, and then thank you all for listening.
Are there questions for Krishna?
Thank you. I was wondering if there'd be an initiative in future for new users, like at the beginning of the year, to, for example, learn how to optimize their scripts, know where to look for example, what nodes are busy, what not, you know, to kill their job before time if it's completed, like before the allocated number of hours they've given before it's completed. Because, yeah, sometimes you submit a job, you think it takes 5 hours, it takes like 1 hour. But then you're still waiting for the rest of the 4 hours thinking it's running. But also, it also takes up time for the person after you, because that 5 hours is still allocated to
okay, so
your job, if that makes sense.
the CHPC currently has their training, right? They've got the summer school and they've got the winter school, where they then teach you how to do this stuff. And I think there's also documents on the wiki. I know Werner can maybe answer the...
Maybe just to say, of course, the summer school, the introductory coding summer school, but that is more on a basic level, say Linux, Python skills. But we do have the winter school that we call more practical HPC. And these are the things that maybe speaks more to what Krishna is doing, where you learn how to scale properly, what to look for. So we have different levels of training. Another training that will be coming in is even at a more basic level, where we talk about induction training, because what we see often at CHPC is we get users that are so unfamiliar with the environment that don't even know where to start. So this will also become more prominent. But what you are talking about, we need to cater for all levels of training. So at the moment, I think what you are talking about is more closely related to our winter school, which has been running still online even this year. So maybe we will get back to a process of, well, some physical hosted event, or maybe a hybrid event. But yeah, we are focused on doing those things.
Thanks. I have a question. So I'm not sure how many of the programs are being run on a regular basis. Is it possible, for example, to train an algorithm to recognize how much time is being used for a specific program? Say, for example, for Guppy, when we're base calling sequencing reads, and then give an advice based on the size of the input data set?
One could probably do that, yes. I must actually, I will have a look and see. We must just check to see which applications are running and things. And yeah.
Thank you.
Got a rather enthusiastic Ernst Berger of Altair who wishes to contribute to that answer.
I think speaking to that question, this is something that we are looking into, is yes, you can have some sort of a machine learning model that looks at data as it comes through the cluster over time and builds up an appreciation of how much time or resource does a particular code or workload require, and then in some sort of advisory capacity, advise a user to say, look, you've requested too much cores or runtime or whatever. Maybe you want to amend your script to help them learn in that way. So that's something we're coming and we can look at with CHPC if we want.
Thank you for your time. So my name is Kim Martin. I'm an SSI fellow. I was awarded one of the first international Software Sustainability Institute fellowships last year. The SSI I'm going to be talking about, I'm going to mention them a fair amount. They're a UK organization that has been funded by all 7 UK research councils. They have a manifesto or a mantra that good software practices create better software, resulting in improved reproducibility and reusability in research. They believe that all researchers should have access to basic software training, and that software should be accepted as a valid research output, so included in metrics, and that there should be reward and recognition for the people who develop and maintain research software and the means to fund their involvement in research. So what is an RSE, or Research Software Engineer? So I first learned of the term mid-2021 at an R conference, and I basically came across it in a keynote talk by Heidi Seibold, and it caught me immediately because I felt this is a description of the stuff that I already do. It's the things that I enjoy doing, and it's also the things that I want to learn to do better. I mean, it's sort of like, as a biomedical science PhD, I kind of have been dogged by imposter syndrome moving into this area the whole time. So the SSI coined this term RSE in 2012 on the recognition that research is increasingly dependent on software, and that such software requires people who combine professional software expertise with an understanding of research. And the rationale behind, I mean, they did not invent the use of software in research contexts. That's been going for as long as there's been software. But what they came to understand is that it's important to have a name that people who do this kind of work can get behind. Because they did a study where they looked at 10,000 job adverts and found 200 different job titles. The logic is that if there is no sort of defined name to describe this role, there's no real career path. And with no career path, there's no real job security. There's no sort of ability for people to develop themselves as having a professional portfolio. You tend to jump around from role to role to role. And without having a defined career path, it's difficult. I mean, academia can be perilous as it is when it comes to, sort of a tenure, say, continuity of employment. But now the problem is on a more systemic level that if individual people do not have good career opportunities within academia, then there is no ground for a sustainable supply of expertise in this area. I mean, I believe Nilesh mentioned in a talk about in deep learning in Daba how, if we're outsourcing this kind of, any particular work elsewhere, there's no ability to build up that expertise nationally. And the typical thing here would be, a PI brings in a postdoc, that postdoc spends their time writing software, they don't write papers, they don't develop themselves and having a potential of an academic career path. They bounce around to different roles, and eventually there's attrition. They get lost to industry, and they get lost to industry without actually having a stable base of skills that will allow them to go in at a higher level. And the software that they leave behind doesn't tend to be written very well because it's based on ad hoc, self-taught skills. The advantages of working with RSEs when we start talking about more professionalization of this role is to researchers, they have the opportunity to maybe do research better, faster, have more success in winning larger grants, more fame if code associated with their work gets cited, and less risk of notoriety, so potentially less risk of retractions if there's any errors in research code. And this is in the context of open science, where there's the understanding that more and more there's this pressure for code that's sort of associated with research to be made available and that can be built on by other researchers. An RSE group, comprises of a number of RSEs who work for researchers across an organization. It gives researchers access to professional software engineering expertise, but they only have to pay for what they need, so they don't have to hire someone into their group with these skills. It is also one way of providing a stable career path for RSEs, because now they have, instead of having to bounce between different, short-term grants and groups, they have a stable home that they can be long-term employed, and there's often permanent contracts associated with these groups in the UK. So the first RSE groups were formed at leading universities in the UK from 2012 onwards. The first one was UCL, which is now a behemoth. It's become its own beast now. There are over 40 RSE groups in the UK, and the number of them internationally is growing. So some exemplar groups include those at Oxford, Cambridge, Princeton, Harvard, and elsewhere in the world. Aalto is one of my favorites, actually. The benefits of RSE groups, again, are manifold. So, for RSEs, stable careers, a peer group, recognition and career development. Research projects get flexible access to expertise. They can share the skills between projects and access to niche skills. And the researchers get opportunity to get help and advice, training, and support with infrastructure. The University of Sheffield I look at them as a case study for how an RSE group might start. So in 2015, they had one member of staff. They kicked things off with a bunch of grassroots initiatives involving training, consulting, and demonstration projects. Then there were some RSE fellowships awarded by the Engineering Physical Sciences Researchers Council, and then additional grants on that. They got increasing support based on the value they were clearly adding, and I say they've been going from strength to strength from there. So RSE Sun, bringing things back to South Africa and Stellenbosch University, which is my host institution at the moment. I've had support at 80% funded last year from the Agroinformatics Initiative at Stellenbosch University. And I was basically responding to discussions that I'd been having with researchers across Stellenbosch, with the kind of concerns that were coming up. So things like concerns about lack of review of code prior to publication, which is potentially a massive reputational risk if errors creep in. Poor quality code, which is difficult to understand or maintain, and the software sustainability of the SSI's name refers to this being able to maintain and build on code. And that leads to loss of time, loss of potential for reuse, reinventing the wheel, all that kind of thing. And then one of the additional problems is just generally lack of coding skills among researchers and students, which limits the ability to generate, manage, and utilize data, and there's a massive opportunity cost with that. So RSC at Sun was founded in early last year. The website is rsc.sun.ac.za. And the 4 pillars of RSC at Sun activity are training, consulting, providing coding support, and community building. At least this has now been the sort of ground plan of where things have been going in the last 2 years. I presented about this at the RSC Society's RSC conference last year in the UK. And the plan had been engaging with the research community about their needs, pilot course services, which I've been doing, and then evolving the model to figure out how to best serve Stellenbosch University as a whole. And my questions then became, well, what options are there for models, and which would work best in the African context? Given that so far, everything was based on, there's a lot of information about what had been happening in the UK. A lot of information, but maybe not so accessible. So I wanted to learn more directly from the UK RSC groups, because I'd only just joined this community, let's say, and I only met members of the community in person for the first time in that conference in 2022. So I had questions along the lines of what works for groups in terms of their context and position within the host organization, their funding model, whether they're centralized, embedded, generalist, specialized. These are all terms that I kind of came across when doing the reading around and talking to people. But then I became very interested in details of the organizational environment, given that what I was learning from RSC group leaders that I was talking to was that it's very challenging to attract and retain, potentially also train, but I think actually attracting and retaining RSCs. And my understanding was that there's a lot to do with the organizational context of the RSC groups that would impact this. So then I was wanting to know, well, what works for the people in these groups? So management practices, the working environment, training and career opportunities. So what I did is I submitted a proposal to the SSI to do what I called the RSC road trip. And the plan was to basically tour around the UK and ask a bunch of questions of interviews of RSCs in these different groups to try and identify what it was that made a difference in their working lives, let's say. So I put this document online to gather feedback from the RSC community for my interview guide. I got a lot of feedback. This document is still online, but there were a lot of good comments that are still there because they make for interesting reading. And the road trip itself started in Manchester, ended in Exeter, took over 6 weeks. I visited 14 different universities, 25 different RSC groups, including talking to several embedded RSCs, I'll talk about just now, 101 interviews and 98 hours of transcribed recordings, which I still need to finish processing. Going through those questions and the answers I was getting, so far I've identified about 105 variables, but this work is very much ongoing. So just to say again, the caution, these are preliminary impressions, analysis is yet to be completed. Also, I'm going to go quite fast through some of this because a lot of this I talked about in more detail in a NETEC talk, which is available as a recording on the NETEC's YouTube account. So if you want to sort of see me talk about this stuff in more detail, that would be the place to go. So one of the things I was talking about looking at was the diversity of RSC groups. And I ended up dividing the groups that I visited into 5 different categories based on 2 different axes. So the degree of specialization of the group, whether they had any degree of specialization of the technical or domain type, and then also where their client base was. So I would say that, as I've defined it, a specialized group provides domain and or technical specialist services to client researchers through the entire organization, like the entire university, all faculties. An independent group applies for funding for RSC-intensive projects that the group co-initiates, working with other research groups collaboratively. So that's maybe projects nucleated around a particular software platform, for example. Embedded groups are employed as a group, and they have an RSC as a manager. So they're the individuals within that group are being managed by someone who has the necessary skills to give them guidance. And they're employed within a subdivision of the host institution, and they provide services to client researchers within that same subdivision. So this might be, say, health faculty, and they'd be based there, and they'd be working only with health faculty researchers. An embedded RSC, by contrast, is an RSC who is employed within an RSC group, but their manager would be maybe the PI. So they're likely being managed by someone who has niche skills in some domain that is not software engineering related. So they don't actually get that kind of real guidance that someone who's being managed by someone with software skills would be able to give them. A central group provides services to client researchers through the entire institution. So they'd be based in IT, and they help everyone from all faculties of the university. And a distributed group, which is quite rare, I only know of two so far, one in the UK and one in the States. Their members are seconded to different research groups for the duration of a project, but they function as a virtual group rather than embedded, isolated RSC. So it's trying to get the best of both worlds. And I visited, the majority of them were central groups that I visited, a bunch of embedded groups as well, central groups and embedded groups, and then I visited one distributed group, one independent group, a couple of specialized groups. Talking about HPC as a context for RSE, so, and this is now caveat, I'm not an HPC person, so this is very much based on sort of secondhand what I've understood from talking to these RSEs. But my understanding is, from the people I've talked to, there are university RSE groups that were nucleated around in-house HPC facilities. These groups tended to be well supported and funded by the host institution, depending on the strategic objectives of the host institution. So for example, if the university in question had the ambition to become the host of a national cluster, they would then provide that RSE group with a lot more support than would otherwise be the case. And that would maybe give them a lot more sort of flexibility in the way the group would operate, the sort of how they use their time. So the bread and butter work of these groups, of the RSEs in these groups, would be promoting use of in-house HPC by researchers, so the consulting, the training, and the project work. But again, depending on the degree of support they receive from the host institution, they might also have the luxury of being able to expand their activities beyond HPC and offer more services to members of the university for free or for cheap. Well, and nothing is for free, but on the books of the university. My understanding is that the UK national facilities in some way cast shade over the smaller institutions in terms of investment in in-house HPC. I got the impression that some of the universities were divesting themselves of HPC facilities in-house because it wasn't considered, the cost, the scalability wasn't actually there, especially with the sort of more powerful machines that are starting to, more powerful, more complex machines that people are starting to talk about taking on. The national HPC facilities, so for example, Archer at the EPCC, which is based in Edinburgh, typically have teams of RSEs who support users, but it does seem that scaling support to newer users can be a challenge, and I think there's been stuff mentioned about that nationally here as well. There is scope for, I believe there's scope for in-house RSEs to serve as a bridge between the researchers and the institutions and the national HPC facilities, but the funding models in this can be quite challenging. Something else that I noted was that HPC skills overlap with RSE skills. So some of the larger UK RSE teams coordinate with dedicated HPC systems teams. So this was something I saw in Manchester, for example, where there was a team that managed the HPC and a team that was doing more RSE work, and they did engage with each other, but they were independently managed. Whereas smaller RSE teams had to maybe encompass the sort of non-HPC related RSE support and also HPC related stuff with the same individuals within the team. And then also to highlight that there's something now called the Universe HPC project, which is at a fairly early stage, I think. It's a collaboration between Edinburgh, Oxford, Southampton, and Imperial, and they're developing a professional training program that is both RSE and HPC skills. Now going back to sort of other findings, preliminary findings of the road trip. So I'm going to skim through a lot of this stuff. Basically, the sort of standard idea of what an RSE looks like, I found a lot more diversity than the view of, male, white, has a PhD in the sciences, named as a co-author on papers, uses these tools. I saw a lot of differences from that. One of the differences I noticed was that a lot of RSEs didn't come from academia or had left academia for time in industry before they returned. This varied depending on aspects of the group, and it appeared that industry experience was very valuable. So there were a lot of differences between the groups. In terms of commonalities, I noticed a lot of internal group practices that did seem to work well. So as far as quality control and continuing professional development, code review, getting people to work together as much as possible, reducing the bus factor, and then things like book clubs and tech talks were considered to be very good where they were happening. Agile was mentioned a lot where it came to management, including things like stand-ups. Attracting, training, and retaining RSEs. So anything that involved bringing in people from outside, so sort of events and internships and secondments and stuff like that, coaching and mentoring, and then providing RSEs who are in the group with what they wanted. And different people want different things. Some people want to stay in an RSE role. Some people want to be able to move into an academic role. Some people want to move into industry. I personally believe that there is this ideal that I'm aiming to get to of an RSE group as a sort of platform for capacity development and increasing opportunities. So I see it that people should be able to come in from a computer science or industry, software engineering background with or without industry experience, as a researcher with or without a PhD. And then with having had training and experience within the RSE group, they should have more opportunities open to them when they decide to leave. So this range here, from self-employed consultant to industry to embedded RSE to academic, and highlighting these two options, the industry and academic, why I think these are potentially good. On the industry side, the RSE salaries in academia are not as good as industry. Having this bridge, this door widened a little bit, might increase that pressure a little bit to, you could argue that is a good thing. There's also people going to an academic position after having been in RSE. Now you have more academics that value the kind of things that RSEs are pushing for. So, for example, good quality code that's easy to maintain and build on. Just to highlight that there's Alto RSE explicitly advertises their group as a good stepping stone for people wanting to go into industry. So they're leading the way here. Different people like different work. So some people want to work very closely with academics, some people don't. Different roles for different people. So some things that came up with the discussions I was having was product owner might be a good role for some people in an RSE group, especially people who are new to RSE and could maybe be paired with someone who's got more software, who's got more strength in the software skills. And then also there was this talk in larger teams of a dedicated project manager role. And I believe that diversity in roles should be a reflection of the diversity of goals. So, an idea of an RSE group is differentiating into these different roles. It would maybe assist people into moving into these different areas. And again, allowing people to move back and forth, leaving to industry and coming back, they bring more skills and experience. Going into an embedded role in a research group and coming back, they bring more connections, more experience, more work in the academic context. Diversity over monoliths. So rather than having a central RSE group that tries to do everything for everyone, potentially what would work better is a sort of hybrid hub and spoke model, where there's a number of different embedded RSE groups that have specialities in different things, and they network quite well with the central group. And this can also involve movement of people back and forth between the embedded groups out to the periphery and then back to the central group, which is maybe a way of allowing skills to develop rather than having sort of little silos of people who don't develop themselves. Again, RSE and HPC, so by analogy of this within a single institution model I'm talking about, where you have, this sort of hub and spoke model of embedded groups with a central group at the same university. I kind of had the thought of, well, at a national level, if you have the CHPC as a national facility that is connected quite closely with RSE groups across different universities in South Africa, there may be some benefits to this in terms of allowing the CHPC helping the HPC to scale its support for the newer users of HPC at these different organizations. And this is by, equivalently in the UK, you've got, for example, the EPCC, which hosts Archer 2, the national HPC facility, and they've got this, they've maintained this network of, they call them HPC champions, which are volunteers at different organizations, and they also are able to work very closely with these established RSE groups, which are now, permanent or mostly permanent collections of people with the right skills who are positioned at these different organizations, these different universities, and can engage directly with the researchers who are local to that university. So just to sort of finalize, so before the road trip, my thoughts were I was trying to establish a sustainable central RSE group with permanent positions at Stellenbosch University. The value proposition I was making an argument for was RSE support for researchers, so better software, better research. And I was thinking that the alternative career options for people who were becoming RSEs would be a virtuous side effect of this. And I've now sort of flipped my thinking quite a lot, where now my thinking is I'm trying to work towards establishing a hybrid RSE initiative, which is combining the features of these central and embedded groups and the distributed RSE groups I was talking about earlier, and aiming to develop it as a teaching and learning platform connected with research software activities. So the value proposition in this case is now capacity development and more RSEs and more career opportunities for existing and proto-RSEs, I call them. And now I see RSE support for researchers and more better research software outputs is just a virtuous side effect of this main goal. So this is actually a word cloud that came from my interview transcripts, and I like that it highlights, think people. I think this is the way to frame this to make the most, to advance things positively. I want to say thank you to the SSI for funding the road trip and much other support, the RSE Society and the community for advice and input and funding for attending this year's conference, the RSE groups who hosted me, the interview volunteers, my bosses who gave me the time to take almost 7 weeks to tour around the UK, and also NETEC for sponsorship to attend this conference and also for the endless support and encouragement. Thank you very much. Before I finish, I would say this is an invitation to join the RSE movement in Africa and beyond, because there is the RSSE Africa, for those of you who are not aware of it yet. It's an African forum for African research software and systems engineers. No membership fees, and you can find their details on this slide. Thank you very much.
Thank you very much for that. I found that particularly interesting and close to home. Thanks for that presentation. Are there any questions? As usual, Quinn, please.
Thank you, Kim. That was really, really interesting. It set off quite a lot of thoughts for me, sitting as I do in a research organization, a little bit with one foot in industry and one foot in academia. So I've got one question just about that. So, I mean, there's always a little bit of dynamic tension in most research organizations between sort of the open science, open publishing kind of approach and trying to monetize artifacts like software as IP.
Yeah.
And I was wondering if you could make a few comments on that and how it would be handled in the sort of RSC context. Because I imagine a lot of those discussions would come back to a group or a person like that.
Yep. So I haven't got the answers, and if anyone here has them, please talk to me. But one of the models that I've been exploring is something called an open source programs office. I don't know if you're familiar with it. So an OSPO, O-S-P-O, open source programs office, is it's a thing that was created in an industry where a company has exposure to open source software, whether it's creating it or using it or contributing or whatever. And the idea is that they would be involved, the people in the OSPO would be focused on how to mitigate the risks and maximize the benefits. The OSPO model has since been adopted in academia very recently. The first named OSPO in an academic context was at Johns Hopkins, and the guy who started it has since been poached by Carnegie Mellon. He's actually, so that's Saeed Chowdhury, he's actually agreed to, I strong-armed him into being willing to be named as a, I'm trying to remember the right term, but sort of on the board of advisors of RSE at Sun. So I've got him as someone to talk to. And my thinking is that it makes perfect sense for an RSE group to be the first port of call for academics who are working with software and have any thoughts at all about the sort of licensing and things like that. That is something that I'm digging into. But yeah, you might want to look more at that as well. But as I say, I don't have the answers. I mean, this is an avenue for finding the answers.
If you do find it, please let us know. And then, maybe a more general question. I mean, this is really fascinating stuff. Do you plan to, once you've digested a bit of the information from the road trip, do you plan to do a road trip around South Africa to the rest of our institutions and explain these concepts to us? Because I think a lot of people in organizations are blissfully unaware of this kind of thing.
Yeah.
That would be really valuable for them to hear about it.
Yeah. Well, I don't know about a road trip to explain stuff. What I'm planning on doing is, as I say, making a concerted effort to digest the information over the next few months and then publish. I'm hoping to, I've got someone in Stellenbosch University who's, so I'd say my background is biomedical science. I've glommed onto someone who's got a background in social sciences and is is a research area that's related. And so I'm hoping to do a proper academic publication about this, at least one. I have thought about doing some kind of road trip around South Africa, but not so much to explain, but more actually to explore what the story is here. And yeah, that makes sense to me. I actually, and I have a particular interest actually in connecting with industry. So where I'm feeling increasingly strongly about there should be a wider door back and forth between academic RSCs and industry. I want to talk to people in industry to find out, how they do things and what they would be interested in and that kind of thing.
Got a question at the back from Mervyn.
Thank you, Mervyn Christophels. I think what you're raising is a topic. I'm saying that. What you're raising is a topic that we discuss at length at the CSPC.
Yep.
And the team that has been here for a while, there is deep-rooted trauma around career pathing, pathways into research support engineering, pathways into system administration. And we discuss at length various options, various models. But I think for me, as I try to understand the landscape around career management as a research engineer, I think the concern for me actually doesn't stem at a vocational. It actually starts way back. And so
it's where? Sorry?
It starts further back where we don't fully grasp what it is to work in the HPC environment. I think if you ask someone at primary school or high school, what is HPC? So I think we're doing a bad job of marketing and campaigning for the space that we're working in. And so when we talk about high-performance computing as an industry with possibilities, what I think we're missing to communicate is that it's broad and it has breadth. And so how do we start to kind of talk about this industry as an exciting vocational opportunity so that we actually start to energize students at varsity, students in matric, to kind of consider a pathway in. I think that for me is something that we need to do more work on. It's actually start to get students interested in, first of all, deciding on a career path into HPC. Because a lot of my staff land up there by, not by probably, I don't want to say by opportunity. It's an opportunity that came about. It wasn't a choice when they were in matric or they were postgrad studies or a PhD. And so I think there's a lot of work we need to do. But I think the other question I had, maybe as a kind of a wrap-up, is that in your experience, what is actually the right career mapping that's going to allow an RSE to remain in the RSE pathway? What are they looking for in terms of the career mapping, in terms of the growth? Are they looking for applied research? Are they looking for opportunities to create new knowledge? Or are they looking for opportunity to support? But I think, for me, I'm realizing it's two different individuals. The one that wants to help the researcher, and the other one that wants to generate new knowledge. The science application versus the actual more pragmatic application. We're trying to bring these two competence together. And I think that's a very unique individual. And we have a few of them at the CSPC, but then they're kind of So that's kind of my question to you. Thanks.
Well, that's kind of the kernel of one of the things that was coming up, like through the talk of. I wasn't so much finding one individual that had both these traits. I was finding people, like some people, as I say, they wanted to be divorced from the rigors of research, let's say. Some of them had fled into RSE because they no longer wanted to be sort of on the academic track and sort of like, beholden to publishers and all that kind of thing. Whereas there were other people who, if you put them on a ticket system, I came across at least one really sad case where there was an RSE who was the kind you're talking about, who wanted to be, they wanted to be deep into the research, and because of some organizational issues, they'd found themselves basically on a ticketing system dealing with, very routine stuff on an HPC system, which I kind of looked at that and I was like, it felt like I was seeing a racehorse, thoroughbred racehorse, yoked to a cart kind of thing. And that again is that sense of you need to make sure that there are opportunities for people to go in either direction. If you're presenting an RSE group as a sort of dead end, like come in here and you'll never get out, it's not attractive to a lot of people. Me, by my personality trait. I like to increase my options rather than decrease them over time. And yeah, you need to make it possible for people to grow and move in different directions. So I don't think it's about trying to find one person who does everything or can think in these different ways. I think it's about bringing people in and identifying what they want, giving them exposure to different avenues, and then enabling. When you're talking about bringing more people in to like youngsters and such, like bringing them into, in your case, HPC, but also RSC. I think what the Alto RSC, I mean, when I was still learning about RSC and still doing my sort of, explore the internet and what do people say, I came across their website. And if I'd been anywhere near Finland, I would have tried to get into their group because they were so attractively phrased as far as I was concerned. So that line in there saying, if you're interested in becoming a scientist developer at a company, but you don't have the skills yet, come and join us, we're a good stepping stone, basically, was hugely attractive. So there's that. And then I think there's also just the manufacturing serendipity of allowing people to get exposure in a way that's meaningful, like not sort of, theoretical or whatever. So I'm very naive about, what I'm actually taking on with what I'm aiming to do at Stellenbosch. But I'm looking at any possible option I can that's going to give, people of different levels, all the way down from undergrad up, like actually engagement in real projects, so they can actually see how things work. There's a sort of like go back to a tribal environment where the little kids learn from the bigger kids. So the typical way people learn now of like put them in a class and everyone's the same level and you've got the teacher at the top. That's like, no, that's not how human beings are designed to learn or find what they want to do in life. So yeah.
Maybe just before I go, I just want to say that I saw the one model where you had the CHPC national facility, and I want to maybe just say as a team, we're happy to engage with you and kind of look at options as to how we can partner together for the future. Thanks.
Great, thank you. Then this talk did its job.
Thank you. I've got one last question, which is, in your research into this, what have you seen from organizations? Because an organization needs to make space for RSC. Right?
Yes.
And how are organizations thinking sufficiently outside of a very small box to make provision for these people?
So like, as I said, the typical model that I was seeing in the UK was trying to find full-time salaries for people in a centralized group. That was the model that I thought was sort of the only model. But when I went to the UK and toured around, the picture, again, this is probably naivete, right? Like, I'm like, I'm not liking what I'm seeing, there must be a different way, but maybe there's not a different way. But I was seeing a lot of sort of, stress on managers to bring in funds from grants to keep these people employed. And then they were trapped in this thing of like, too much work, not enough work, having to grow all the time, having to bring in more work all the time. So the typical thing would be trying to get researchers to write the RSCs into their grant applications. The RSCs that are in the group now with salaries that need to be continually paid. They have to ask for more, they have to get more researchers writing grants than they have RSCs because grant applications are not that successful all the time. Like, 40% maybe is a good... so now they have to start turning down work. But now they also need to start growing once they started building that demand, they need to now start, meeting it more and more. And just the sense of an absolute rat race of this weird balance that you're trying to strike. And I mean, I guess, let's say, the reality of the world, I guess that's what starting a business would be like outside a university environment. But, we're a university environment, surely we can do things in a way that's a bit different. Hence this idea of the distributed model, it's a little bit more attractive to me, where I'm looking at people who already have positions, but lack the opportunities to develop their skills. So I'd be looking, for example, at postdocs, who are doing more of the RSC type stuff, find that they prefer software to papers, want to be part of a group that they can then learn and grow their skills and then develop those alternative career pathways if they choose to follow them. But as for what universities are doing, it's sort of related but parallel. I'm part of an international working group called Pro4RS, Policies for Research Organizations in Supporting Research Software. And the aim of this project over the next, say, year is to identify what policies in research organizations are good for supporting research software and by extension RSCs. So maybe I'll have a better answer in, a while.
Thank you very much.
Thank you so much. So first off, I would like to thank the CHPC team for organizing this conference and for Dr. Werner Janssen van Rensburg for inviting me as a speaker. So as I've just been introduced, my name is Sarah Roef and I am a researcher at the Agrometeorology Division of the Agricultural Research Council. And today I'd like to present to you on some of the work that we're doing to dynamically downscale the CMIP6 climate model projections. So as I mentioned, I'm part of the Agrometeorology Division, and we, in essence, we sit in Pretoria, part of the Institute of the Soil, Climate and Water Research Institute. And our activities there all rely on climate data. And the big question is climate change, and how climate change is coming to impact agricultural activities, and how agricultural activities are looking to impact on climate change. And this is where we sit in the Agrometeorology Division. We are focused on trying to understand this intersection between agriculture and climate and weather. And my role there is understanding climate change and how climate change is impacting on agricultural activities. And for us, we are in desperate need of data towards decision making. So we know that temperatures are increasing over Southern Africa. And with this comes changes in extreme temperature characteristics and increases in heat waves, for instance. What does this bring? It can cause crop failures, it can impact livestock, and it can also impact human health. And this is particularly human health of farm workers who work outdoors. Then we also need to acknowledge that across South Africa, rainfall patterns are changing, and the extremes are emerging quite substantially. So we're seeing a lot more drought, and we're also seeing changes in extreme rainfall events, such as more frequent flooding events, particularly over eastern regions of the subcontinent. And all of this boils down to potentially leading to food shortages in the future. And we've seen in many places that there have been some food shortages, and for us to actually plan for this and to make decisions in a warmer world, we need data. And we can rely on global climate model projections, if we like, to provide us with information which will provide us scenarios of how future climate patterns may change. But unfortunately, these are very coarse. And here are just some 4 model projections looking at the 126, the 245, and the 585 future scenarios. And essentially, these are different levels of greenhouse gas mitigation. And as you can see, that the figures here are quite blotchy. So these global climate model projections, they are very coarse, and they also differ in terms of rainfall quite substantially across the various models. So for us, this kind of information and this information at this resolution is not yet suitable for decision making in the context of agriculture. So what we're trying to do at the Agricultural Research Council is create a data set that in essence can help us with this decision making. One where we can account for various different sorts of scenarios in terms of rainfall changes. As you can see, this CAN ESM model is projecting drier conditions, but come to the SP 585, and this model is projecting wetter conditions over eastern regions of the country. So we need to look at an ensemble approach. And this is boiling down to the activities that we are undertaking at the ARC. So I thought it would also be interesting to show that even with temperatures, there are quite vast projections across the different models, and still it's very blotchy in these images because we're dealing with coarse resolution data. So for us, we are trying to downscale this data. So we're trying to take this coarse resolution global climate model data, and we're trying to provide this data set at a higher resolution so that we can use this for informed decision making, so that we can consider thoughts about should we communicate to farmers that there's a need for changing crop types maybe, or changing the timing of cropping activities, or perhaps just aborting livestock activities in an area because it's just going to get too hot. So we need this kind of information, and we cannot get this information from coarse model outputs. So here's an example of a GCM output, which is from a global climate model, and here is an output from a regional climate model. So this is showing elevation, and I think this image really highlights the reason why we need to downscale these outputs. And in essence, if you see the topography, when you are running a simulation, your topography is at the resolution of the simulation you run. So if your simulation is at 8 kilometers, so will your topography be at that resolution, whereas if your simulation is at 100 kilometers of a grid cell resolution, your simulation will also be at that sort of resolution. So for us, over the eastern regions of Southern Africa, particularly with the escarpment areas and with the Drakensberg area, what do you think this is going to do in terms of projections of rainfall? This means that we'll struggle with these projections, but at a higher resolution, we might better resolve these projections for rainfall. So this is a big underlying reason as to why we are downscaling these GCM outputs. So I thought for non-climate modelers out there, it would be important to highlight two very, very traditional downscaling approaches, and one is the dynamic downscaling approach, which is the approach that we are undertaking at the ARC, and the statistical downscaling approach, which is the one that we are undertaking, which is not the approach that we're undertaking. And so the dynamic downscaling approach is an approach where you use a regional climate model. One can use a uncoupled model, one can use a coupled model, and essentially you drive this model with boundary conditions to provide you with resulting outputs. And for us, we are using an atmosphere-only model, as I'll highlight in later slides, but we can also use a statistical downscaling approach. And what's very beneficial about the statistical downscaling approach, but can also be a drawback of it, is that it is not very computationally expensive, because one can downscale only single variables. But when it comes to the dynamic downscaling approach, we're basically running the model simulation again to provide a whole suite of variables. And unfortunately, it's very computationally expensive. But there are lots of benefits about it. We can simulate the different types of climate mechanisms. We don't make assumptions about how the future climate is related to the past, the present climate. And of course, it is not as computationally cheap, and one drawback of it is that we do not correct for biases. So still there's a later process to correct for biases. So this is a massive undertaking, and as I mentioned, it's very computationally expensive, and the results rely very heavily on the parameterizations that we choose. I'll elaborate further on these in a later slide. And of course, as I mentioned, the biases are not corrected. Let me move on here. So this is the process that we're running. And we are using the CHPC resources quite intensively. We are running some of the work on our own local workstations, like the actual pre-processing of the GCM data. We're running this on our workspaces. So, whoopsie. So this is preparing this GCM data just to ready it basically for the simulation. Then we've also prepared the grids on our own local computers, and the rest of the tasks are starting to become large, especially because of the length in which we're running these simulations. So we have to move these onto the CHPC. So this next task that we do, so we first start with the pre-processing of the outputs, and then we move to create the grid of our output, the grid in which we'll run our simulations. And then we ungrib the data, which is basically which is basically transforming the data into a form that our numerical model will basically understand, and we're using the weather research and forecasting model, the WAF model. And in essence, then the next step as well, all of these, the remaining steps have to be run on the CHPC, while our next step of the Python post-processing, we've got a tool that we've sort of not necessarily developed, but we're piggybacking off some existing tools to process the data, and that we can do on our own local machines. But this process, in essence, is on the CHPC. So for us, the CHPC is extremely valuable for our activities. If you think about a numerical model, you're basically solving different types of equations at different time steps. And all of you have computational backgrounds, so I won't really go into detail. But in essence, in some instances, for coarse resolution model, you can solve up to 73 trillion calculations for a 100-year period. So for this, we need the CHPC resources because it'll never run on our local computers. So to detail some of our downscaling work, I thought I'd show you guys the actual configuration that we're running and the area that we're simulating. So we're running a WAF model for 2 domains. So we have a parent domain, which is this outer domain, and then we have a nested child domain. And our parent domain, we're simulating the outputs at a 40-kilometer resolution. And why we've chosen this domain is so that those who are interested in understanding dynamics associated with tropical systems residing in the tropics, or perhaps westerly derived systems which are mid-latitude based systems, or perhaps some people are interested in the subtropical high pressure systems. So our domain is positioned large enough so that we can study dynamics of the weather systems. Then we have a higher resolution child domain which sits over the Southern African domain, the Southern African region, and it's simulating at an 8-kilometer resolution, so that in essence we can visualize rainfall at a higher resolution. Sure, it's not a high resolution if you think of it, because we're still not able to resolve processes like convective storms that can be less than 1 kilometer in size, but it's much better than the GCM outputs. And we're providing a data set at 35 vertical levels. I'm not going to go into detail about the vertical levels, but let me talk about the time frames. So our historical simulation, we're looking at a simulation of 1980 to 2014, and then we're running 3 future scenarios, the 126, 245, and the 585, which in essence are describing in a nutshell varying levels of greenhouse gas mitigation. And we're running these for the 2015 to 2100 period. So what we're doing on the CHPC is we're running 2-year simulation periods, and then we're reinitializing our model runs with restart files. So basically, it takes extremely long. And we, of course, cannot resolve all the processes, as I mentioned, because our 8-kilometer resolution, for instance, is not good enough to resolve cumulus convection processes. So we do have to apply some parameterizations to it. Oh, I actually wanted to highlight the reason why we've chosen a nested domain is just so that our domains can talk to one another, so that we can try to produce more accurate results. It really helps to get them chit-chatting across the simulation so that these rainfall outputs are at least more accurate and they're produced they're just produced better. I'll show some results of that. But anyways, coming back to the parameterizations, we have various types of parameterizations that we've chosen, and how we've decided on these parameterizations is we've used the CHPC to essentially run different types of experiments, from experiments looking looking at average rainfall patterns to experiments looking at extreme rainfall events to drought events, to heat wave, as well as to cold wave events and to average temperatures, so that we can try get a range of parameterizations that can provide as accurate outputs as possible. And of course, we've relied on the existing academic literature because there have been many experiments undertaken and we could already throw out many different types of parameterizations as a result. So we are quite restricted in the actual models that we can downscale. The WAF model is very particular in what types of variables are needed for input, and we can only downscale a model that has the available minimum initialization variables. So we found that only 11 out of I think it was a good 50 to 60 odd models can be used, which is quite sad, but 11 for the win. So these minimum initialization variables, this is just a list of the variables that we rely on, which is 3D and 2-meter air temperature, skin and sea surface temperature, 3D and 2-meter relative humidity or specific humidity, various wind components at the 10-meter and the 3D levels, surface pressure, mean sea level pressure. We also rely on soil moisture and soil temperatures, as well as various other types of land surface variables. And then as for our outputs, we are obviously going to have this data set that we hope will be a public good data set. So those of you who are interested in understanding understanding climate change in relation to your activities and in relation to future projections, we hope that we can share this data with you once it's finally ready. But some of the outputs, of course, is these minimum initialization variables. As well, we also will have precipitation, things like shortwave, longwave radiation, and many other variables can come out of this. We can also calculate a lot of different types of variables. And of course, we'll start off with variables that are important within our agricultural research. But, we're open to the idea of other variables that researchers and industry users may need. Then I thought I should just share some results. So, because we're trying to make this method as reproducible as possible and as consistent across the models, we are not yet at the stage where we have many results, but here are some few results that we can present on. And this is just a 1 to 5 January simulation that we have. Basically, you can see that the simulation is really the WAF simulation that we have. This is the 8K simulation, the child domain. It's just really at a higher resolution. We haven't yet gone into evaluating the outputs yet, so this is, of course, another step coming in. But so far, things look quite good. And we can carry on, basically, and if we find that the outputs are pretty useless, we can adjust thoughts as well. So there's no train smash there. And here's some other results for a later period. We did some few experiments really just to see that our parameterizations were still good with these coarse resolution outputs. And we found quite decent results. I haven't necessarily, this is all I've presented in terms of the results. But I thought I should also highlight some challenges. We've had an immense amount of challenges. We have a small team, and we do not have a lot of hands on deck. And the team that we do have, we've all had to be trained in terms of basically doing this. So a lot of us are also quite new at high-performance computing. But we're getting there, and it's really great stuff. We've got some trouble as to where to store the data set, because it's very big, but we're making strides. And we have, of course, a lot of future plans. So we hope that this data set that is uncorrected will be ready by about June or July, perhaps. And then we want to bias correct the results. So we can provide a user with an unbiased corrected data set as well as a bias corrected data set. So machine learning for the win.
there are so many machine learning presentations here, so I thought I definitely need to highlight to you that we're perhaps looking for a PhD student who has some great machine learning background, if there's somebody out there. And yeah, thank you so much. I first want to acknowledge my two colleagues. They have been instrumental in this work. They're really fantastic. This is Mokove and this is Murandeni. Yeah, they're really great and they're working hard. And then I just want to thank the CHPC for all the resources. I hope that we are not one of the misusers. And I promise we shall optimize our processes. We are attending the CHPC courses so that we can improve on it. And yeah, so thank you so much. And yeah, are there any questions or comments? Oh.
Yeah, I think that's a wonderful, brilliant presentation. Of course, I've done some projections, but not with WAF. So the question is, for the WRC, what do you call it? ARC. So in the model output, have you explored the stream flow output, like river runoff, water, does stream flows, because it's very, very important for seasonal forecasting and for agriculture. So I just want to know if you've explored that or whether you've got plans to explore that part whereby you, because I believe from the DFFE or from the DWS you can get the stream flow climatology, which you can actually ingest in the pre-processing so that you can improve on your seasonal rainfall forecast. Thank you.
So we haven't done that yet, and we weren't necessarily going to consider it. Our goal here is we're taking the CMIP6 outputs and just downscaling them, but that is a relevant thought, and perhaps that's worth chatting about further, actually. Thank you, Robert.
Right, Nikki's question essentially, you did mention the challenges of storing the data. How are you getting on with getting data into DERISA? Or what are your plans for dealing with longer term storage of your results?
So the ARC really wants the data set to be stored internally. And that's where we're having our challenges, because as much as they want that, they're also a little difficult sometimes. So basically there are plans internally to store the data set, and they're quite set on it must be internal.
Yeah, that's surprising. Thank you.